Hey, take a look around you. I mean, really look. The screen you're watching this on, the air you're breathing, even you. What is all of this stuff really made of? Well, in this explainer, we're going to go on a journey to find the absolute fundamental building blocks of our reality. So let's dive right in. You know, it's a question we've been asking for thousands of years. If you could just zoom in, and I mean way in, past your skin, past your cells, what would you even find? That's the trip we're about to take, from the world we can see and touch, down to the invisible world that makes it all happen. So, where does our journey to the smallest of small begin? Well, it starts with a single, incredible particle that makes up all the matter around us. It starts with the atom. Say hello to the atom. Seriously, think of it like the universe's ultimate Lego block. It is the smallest possible piece of any element, so tiny you can't see it, obviously, but it's the absolute star player in every single chemical reaction. For the longest time, atoms were just a cool idea. But then this guy, John Dalton, came along and basically wrote the first official rulebook for them. He laid it all out. All matter is made of these tiny particles. All atoms of the same element are basically twins, and they combine in simple, predictable ways. But here's the kicker. You can't create or destroy them, you can only rearrange them. This was a game changer that turned chemistry into a real science. But here's the thing about atoms. They're kind of like social butterflies. They very rarely just hang out by themselves. So what happens when they start teaming up? Well, that's where the molecule comes in. When two or more atoms decide to join forces, when they're chemically bonded together, they form a molecule. And this is the next level of complexity on our little journey. And these little atomic teams, they come in two main flavors. First, you've got molecules of elements. This is where identical atoms pair up. A great example is the oxygen we're breathing right now, O2. Then you have molecules of compounds. This is when different atoms get together to create something totally new, like water, H2O, or carbon dioxide, CO2. Okay, now things are about to get really interesting. See, atoms have even smaller particles zipping around them called electrons. Usually, everything's perfectly balanced. But sometimes, an atom can gain an extra electron or lose one. And when that happens, bam! It suddenly gets an electrical charge, and it becomes something totally different, an ion. And there are two types of ions. If an atom loses an electron, it ends up with a positive charge, and we call that a cation. If it grabs an extra one, it gets a negative charge, and we call that an anion. The perfect example? Good old table salt, NaCl. It's just a sodium cation, Na+, and a chloride anion, Cl-, stuck together like magnets because of their opposite charges. Cool, right? All right, so we've met our main players, atoms, molecules, and ions. But what are the rules of the game? Turns out there are two fundamental, unbreakable laws that govern every single chemical interaction in the universe. Rule number one comes from Antoine Lavoisier, and it's the law of conservation of mass. The easiest way to think about this is like cosmic accounting. In any chemical reaction, you can't just make matter appear out of nowhere, and you can't just make it disappear. Everything has to be accounted for down to the last atom. I mean, it makes things super simple. If you start with 10 grams of stuff A and mix it with 5 grams of stuff B, guess what? You are going to end up with exactly 15 grams of product. No more, no less. In the universe's giant chemical factory, nothing ever gets lost in the mail. And the second big rule, this one's from Joseph Proust, is the law of constant proportions. If the first law was about accounting, this one is all about consistency. It's the universe's guarantee that a specific compound will always have the exact same recipe. Just think about water. Water is always water. It doesn't matter if it's from your kitchen tap, a fancy bottle, or a comet flying through deep space. Its recipe is set in stone. Hydrogen and oxygen, always in a precise 1:8 ratio by mass. This law is the reason chemistry is so reliable and honestly, so beautiful. So, with these solid rules in place, chemists needed a way to actually talk about all these combinations, right? So they developed a kind of secret language, a special shorthand to describe molecules and reactions without writing a whole novel. Part of that language is a concept called atomicity. Now that sounds super fancy, but it's just a word for counting how many atoms are in a single molecule. So a helium atom flying solo, that's monoatomic. The O2 we breathe, that's diatomic. And ozone, O3, which protects us from the sun, you guessed it, triatomic. It's really that simple. And this brings us to the system for writing the recipe for any compound, its chemical formula. And it's basically a simple 4-step trick. You write down the symbols. You note their valency, which is just a number representing their combining power.
Then, and this is the clever part, you crisscross those numbers. They become the little subscript number for the other element. So for aluminum and oxygen, aluminum's 3 and oxygen's 2 just swap places, and you get Al2O3. It's a neat little system that just works.
And this secret language also lets us figure out the weight of any molecule. It's called the molecular mass, and you just add up the individual atomic masses of all the atoms inside it. So for our old friend water, H2O, you take the mass of 2 hydrogens, add the mass of 1 oxygen, and you get a grand total of 18 atomic mass units. Easy.
Okay, so this brings us to our final, and maybe biggest, challenge. We know atoms are impossibly small, and there are countless trillions of them in anything. So how on earth do chemists actually work with them? How do you count something you can't even see?
The solution they came up with is nothing short of brilliant. It's called the mole. And just like we use the word dozen to mean 12 of something, like eggs, chemists use the word mole to mean a specific but very, very large number of particles. You can think of it as the chemist's dozen. So just how big is the chemist's dozen? Well, get ready for it. It's this number, 6.022 times 10 to the power of 23. That's a 6 with 23 zeros after it. It's a number so mind-bogglingly huge, it's hard to even imagine. And it's so special, it has its own name, the Avogadro number. But here's why this number is so important. This one number, it's like a magic key. It's the bridge that connects the invisible, microscopic world of a single atom's mass to the big macroscopic world of grams. You know, something you can actually hold and weigh on a scale in a lab. The mole is the idea that makes all of modern chemistry possible. So there you have it. We've gone from a single, tiny atom to the rules that govern them and even figured out the secret to counting them by the trillions. It's like we've learned the alphabet and the grammar of the universe itself. So the only question left is, now that you know the language, what stories are you going to see playing out in the world all around you?